All right, welcome back to another lecture. We're going to cover section 3.5 in this one, and we're going to move on to two-sample hypothesis testing starting in 3.5. And in this section, we want to talk specifically about two-sample hypothesis testing when what we're testing are proportions. So far, of course, we've learned about testing one parameter at a time, and we've talked about tests for proportions and tests for means. But a much more common scenario is that instead of trying to compare a sample proportion that we're getting to some kind of claimed population proportion, it's actually usually much more common that what we're going to be doing is comparing two sample proportions to each other or two means to each other. So let's get into it, right? There are lots of tests that we could run depending on the number, type, and relationship between the parameters that are being tested. And we're just going to, in this section, talk about inference on two proportions. So we're going to introduce the two-sample proportion test. Now, the steps for the hypothesis testing here are the same as they were for one-sample hypothesis testing. Really, the only thing that's different is how we get the p-value, okay? And so without further ado, here it is. Since we're talking about two samples, we're going to use subscripts to help us distinguish between the samples. So P1 will represent the population proportion of group 1, and P2 will represent the population proportion of group 2, and so forth, right? N1 is the sample size of group 1, N2 is the sample size of group 2, and so forth. So with that in mind, here's the two-sample proportion test in all of its glory. One thing that you'll notice right off the bat is that actually the null and alternative hypotheses are, in my opinion, a little bit easier to state in the case of a two-sample test than they were in the case of a one-sample test, because the null hypothesis is always going to be that P1 equals P2. We don't have to try to figure out P equals some number and try to look through the problem to see what the number is, right? The null hypothesis is literally always just going to be that P1 equals P2. Of course, we have two different samples that we're comparing, and so we'll have two sample proportions to compute for step 2. But then otherwise, we're just going to use the apps from ArtofStat to get the p-value, so that's not going to be any more difficult, right? The app that we want to use is called Compare Two Proportions, and I'll show you where to find it from the ArtofStat website. If you want a discussion for what ArtofStat is doing behind the scenes to compute the p-value, then you could click on this link right here and read through the material there. There are conditions that we have to check to run this test, and they're the same conditions that we had to check before, right? Little n has to be no more than 5% of capital N, right? So our sample size can be no more than 5% of our population size, and that's true both for group 1 and for group 2, right? And then also, n times p times q needs to be bigger than or equal to 10. And again, that's true for group 1 and for group 2. As usual, checking these conditions is not going to be a big emphasis in this class, so I'm not going to waste any time doing it in the examples. You might have a homework problem that asks you to check these things, but we've checked these conditions before. They're the same conditions that we had to check for the one sample proportion test, which were the same conditions that we had to check to make sure that p hat was normally distributed back in chapter 2. So we've been doing these kinds of things before, and it's just not going to be a huge emphasis. It should go without saying, though, that if the conditions are not met, then the results of the hypothesis test are not valid. So in the real world, you would definitely want to check to make sure that these things hold. Okay, let's dig in. I have two examples for you, but we're going to stretch these examples as much as possible, and we're going to try to get a lot of information out of them. So the first one says, Johns Hopkins researchers conducted a study of pregnant IBM employees. Among the 60 employees who worked with glycol ethers, 20 had miscarriages. But among 750 who were not exposed to glycol ethers, 120 had miscarriages. At the 0.01 level of significance, test the claim that the miscarriage rate is greater for women exposed to glycol ethers. Okay. Well, in order to run this test, we're going to be comparing two groups, right? Women who were exposed and women who were not exposed. By the way, glycol ethers are found in certain cleaning supplies. So anyway, we want to compare these two groups of women, and so we need to label them. We need to label one of the groups group 1 and the other group 2, And it doesn't matter which is which, honestly, as long as you remain consistent as you're doing the problem. So I usually just label the first group mentioned as group 1. In this case, it says among the 60 employees who worked with glycol ethers. So I'm going to call the glycol ether group group 1. And then the group that was not exposed to glycol ethers, I'll call that group 2. And we're asked to test the claim that the miscarriage rate is greater for the women who were exposed. So we want to know if group 1 has a greater miscarriage rate than group 2. Let's see. So the null hypothesis would be that no, there's no difference in their miscarriage rates, right? The proportion of women who experience a miscarriage is the same in both groups. The alternative hypothesis is that the miscarriage rate for group 1 is greater than the miscarriage rate for group 2. Okay, so that's step 1 of our hypothesis testing procedure. Now, step 2 is that we want to get the sample proportions for each of those groups. So let's see if we can figure that out. Sample proportion for group 1, well, there were 60 employees in group 1 and 20 of them had miscarriages, right? So that's 20 out of 60. That's the miscarriage rate. I don't even need a calculator for that. I know that that's 1/3, right? Which is about 0.333 if I round to 3 decimal places. Let's see for group 2. For group 2, there were 750 women in that group and 120 had miscarriages, right? So 120 out of 750. And let's see. So 120 out of 750 is exactly 16%. Now, just comparing those numbers for a second, it looks like group 2's miscarriage rate is much smaller than group 1's miscarriage rate. In fact, group 1's miscarriage rate is more than twice as large as group 2's miscarriage rate. So I would say something is happening, right? I would guess that we're going to reject the null hypothesis and say and end up concluding that yeah, P1 is actually bigger than P2. But there's only one way to know that for sure, and that is to get the p-value. So in step 3, we're going to run the compare two proportions. Okay, we're going to use the compare two proportions app from Art of Stat. When we do that, we'll have to enter in the sample size for both groups. So for group 1, the sample size was 60. And we'll also have to enter the number of successes for both groups. So for group 1, it was 60. Sample size was 60 and number of successes was 20. For group 2, the sample size was 750. And the number of successes was 120. So let's head over to Art of Stat and see what we get. Okay, so I'm going to go to Art of Stat. I'm going to go to Web Apps. And I'm going to scroll down. I have to scroll all the way past my 1 sample tests because I'm going to be comparing 2 groups now. So I have to come down here to confidence intervals and tests comparing 2 groups. And I want to compare 2 proportions. So that's the test that I'm going to select. Okay, I'll dismiss that. And I have some sample statistics to enter. Okay, so for group 1, the sample size was 60 and the number of successes was 20. For group 2, the sample size was 750 and the number of successes was 120. What's really nice is that they give you all this information up here. They compute those sample proportions for you that we did by hand a second ago. They also give you a bar chart comparing the 2 groups so you can see how much of a difference there is between them. We don't want a confidence interval just yet. We want to run a hypothesis test. So I'll choose significance test. And you don't need to check this box or anything. You can just leave that as is. The only thing you do need to change is the alternative. We wanted to know if group 1 had a larger miscarriage rate than group 2. So make sure that this alternative is going the right way. You can see the alternative hypothesis here. You can also see it here. Okay, right here it's saying P1 minus P2 is greater than 0. But that's equivalent to saying that P1 is greater than P2, which is the way that we wrote it down on our page. Okay, so I think this test is set up the way that we want it to go. Our p-value is 0.0003. Okay, so let's write that down. Okay, a very small p-value. So we're going to go ahead and reject the null hypothesis, right? 0.0003 is less than 0.01, which was our level of significance, right? So we reject H null. And then finally, we can write out a conclusion. Since we're rejecting the null hypothesis, that means there's evidence to support the alternative. There is sufficient evidence to conclude that the miscarriage rate is greater for women exposed to glycol ethers. Okay, and that's it, right? That's a two sample proportion test. As you can see, very similar to the one sample proportion test. And so hopefully by now this kind of thing is starting to feel like second nature to you. But let's answer some follow-up questions. Part B says, what does the p-value mean in this scenario? Well, our p-value was 0.0003, and the p-value has the same meaning here as it did for our one sample tests, right? It means this is the probability that we would obtain a difference in our sample proportions as large as the difference that we observed if, in fact, the null hypothesis were true. So in this case, if, in fact, the proportions were the same, right? So there are a whole bunch of different ways that you could phrase that. I'm just going to say, if we assume that the miscarriage rate is the same for these two groups, then there is a 0.0003 probability of obtaining two sample proportions as different as the ones that we obtained. Okay, and of course 0.0003 0.0003 is very small, right? That's a very small probability, right? So it's highly unlikely that we would have observed sample proportions as different as what we observed if the null hypothesis were true. And so we reject the assumption that the null hypothesis is true, okay? Part C, construct and interpret a 99% confidence interval for the difference in miscarriage rate between those exposed and not exposed. Comment on the relationship between the results of your hypothesis test and this confidence interval. Let's head back over to Art of Stat. In Art of Stat, the only thing that we need to change is we need to change the type of inference from a significance test back to a confidence interval. Now, we tested our hypothesis at the 0.01 level of significance, which means our level of confidence has to be 0.99, or in other words, 99%. Remember that the level of significance and the level of confidence should be complements of one another, okay? So we want a 99% confidence interval, and here's what we're getting, 0.0, let's round to 3 decimal places, okay? So we'll call this 0.013. to 0.334. Okay, 0.013 to 0.334. Okay, so there's our interval. We were asked to interpret it. Okay, so we'll say we are 99% confident Now, let's talk about what this interval means. A lot of times students think that this is an estimate for P1 and that this is an estimate for P2, but that is not correct. In fact, what this confidence interval is the entire thing is an estimate for the difference between P1 and P2. So what this interval is saying is that there is somewhere between a 1.3% and a 33.4% difference between P1 and P2. Okay, that's what this interval is saying. Another way to phrase that is to say that we're 99% confident that the proportion or that the miscarriage rate is somewhere between 1.3% and 33.4% higher for those exposed to glycol ethers. So that's the way that I'll phrase it. But there are multiple ways that you could phrase that, right? So we are 99% confident that the miscarriage rate is somewhere between 1.3% and 33.4% higher for women exposed to glycol ethers. Okay, so the hypothesis test answered the question, is there a difference in the exposure rates, or sorry, in the miscarriage rates? And the answer was yes, right? Essentially, the answer was yes. There's a difference in these two groups. The confidence interval is telling us how big that difference is. And what we're saying is that the difference is somewhere between 1.3% and 33.4%. That's actually quite a large gap. That's a very wide confidence interval. And we'll talk about that. We'll talk about why that is in a second. But what's the relationship between this, the result of our hypothesis test and our confidence interval? Well, as I just said, the hypothesis test told us if there was a difference, and the answer was yes. And the confidence interval is telling us how big the difference is, right? I suppose one thing that ought to be pointed out here is that 0 was not inside of this confidence interval, right? If 0 were in the confidence interval, you would get a negative number on the left and a positive number on the right. Why am I pointing that out? Well, because if 0 were in the confidence interval, then we would not be able to safely conclude that there's no difference between the proportions, right? In other words, if 0 is a good estimate for the difference between P1 and P2, then that means that P1 and P2 could very well be the same thing. But 0 is not a good estimate, right? 0 is not inside of our confidence interval, and therefore we can safely rule out the idea that P1 and P2 are the same thing. So maybe I'll say that. Note that 0 is not in the confidence interval. So P1 minus P2 cannot be 0. So P1 cannot be the same thing as P2. Okay, I'm speaking very loosely here. It is, of course, possible that P1 and P2 are the same thing, but we just so happened to get a sample that was kind of unusual. But what we're saying is that that's highly unlikely, right? So 0 is not in the confidence interval. Well, this corresponds nicely with the results of our hypothesis test, right? So which verifies that we should indeed reject H null. Okay, because H null was positing that P1 equals P2. And we're seeing, well, no, because if that were the case, then 0 would have been in our confidence interval, and it's not. Okay. All right. Part D. Comment on the statistical and practical significance of being exposed to glycol ethers during pregnancy. Should pregnant women be wary of glycol ethers? Okay. So, well, the results are statistically significant for sure, right? Because we rejected the null hypothesis. Okay. So the results are statistically significant because we rejected H null. Now, are the results practically significant? Well, it's kind of hard to say, right? Because on the lower end of our estimate for the difference, there doesn't seem to be that much of a difference in the miscarriage rate. But on the upper end of our estimate for the difference, there's a huge difference in the miscarriage rate. What I would maybe point to are the differences in the sample proportions, right? In group 1, the miscarriage rate was twice as high as the miscarriage rate for group 2. So you could say, women who are exposed to glycol ethers are twice as likely, right? So as far as practical significance is concerned, I would argue that yes, there is some practical significance here. So the results are practically significant because the difference is large. Right? Women exposed, or we'll say the women in our sample, who were exposed were twice as likely to have a miscarriage. Okay, and now I'm kind of out of room to answer this question, should pregnant women be wary of glycol ethers? But I think it's heavily implied by what I just wrote down that yes, right? Women who are pregnant should avoid glycol ethers because they're twice as likely to experience a miscarriage if they're exposed to glycol ethers. Now, of course, this data might be made up, right? So you got to take this with a grain of salt. I'm not like a medical doctor or anything, but if this were real, like if these were real data, then I would say, yeah, pregnant women, steer clear of glycol ethers, right? Okay, part E. What do you think is the cause of the confidence interval being so wide here? Yeah, we noted earlier that our confidence interval was very wide, okay? So why is that? I think that the reason for that is because we had a small sample size for group 1, right? For group 2, the sample size was fine, 750. But for group 1, the sample size was only 60 individuals, and that's a pretty small sample size when you're testing proportions. When you're testing means, a sample size of 60 is decent, okay? But when you're testing proportions, generally speaking, we need much larger sample sizes in order to get good estimates. So I think that's the problem, right? So group 1 had a fairly small sample size. So we can't get a very precise estimate. Just to be clear, if both groups have a small sample size, it would still be an issue. I'm saying this because sometimes students think that the reason we're getting a wide confidence interval is because the two groups had such a big difference in their sample sizes. It's not the difference in the sample sizes that matters. It's the fact that at least one of the sample sizes was small, right? If they were both small, then there wouldn't be much of a difference in their sample sizes, but we would still have a very wide confidence interval because of the small sample size issue. So what we need in order to avoid a wide interval is large sample sizes in both groups, right? So it's the small sample size that's the problem. Okay, so that'll do it for example 1. Let's move on to example 2. You're really glad that we only have 2 examples, because otherwise this would take forever, right? Because we have a lot of stuff that we're talking about. But let's take a look at this next one, and then we'll call it good for this lecture. But it says, in clinical trials of Nasonex, 3,684 adult and adolescent allergy patients were randomly divided into 2 groups. The patients in group 1, the experimental group, received 200, I think that's micrograms of Nasonex, while the patients in group 2, the control group, received a placebo. Of the 2,013 patients in the experimental group, 547 reported headaches as a side effect. Of the 1,671 patients in the control group, 427 reported headaches as a side effect. Part A. Is there evidence to conclude that the proportion of Nasonex users that experienced headaches as a side effect is greater than the proportion in the control group at the 0.05 level of significance? So go ahead and pause the video and give the whole thing a try. Go ahead and run all 5 steps of the hypothesis test here. Okay, here's my solution. Okay, so the null and alternative hypotheses should be these that I've written down, right? Nasonex users I'm calling group 1. And we want to know if their proportion of headaches is greater than the proportion in the control group. So P1 greater than P2. For group 1, the sample proportion would be, well, there were 2,013 individuals in group 1, right, in the Nasonex group, and 547 of them reported a headache as a side effect. So that comes out to about 0.272 if we round to 3 decimal places. For group 2, it would be, there were 427 who reported headaches out of 1,671 patients. And if you type that into your calculator, that comes out to about 0.256, right, if you round to 3 decimal places. So now for step 3, we're going to go to inference for a proportion. And we're going to enter sample size for group 1, number of successes for group 1, sample size for group 2, number of successes for group 2, and then we'll see what the p-value is. So let's head over. Okay, sample size for group 1, 2,013. Number of successes for group 1, 547. Sample size for group 2. And number of successes, 427. Okay. And we want to run a hypothesis test. We want to see if P1 is greater than P2. And we're getting a fairly large p-value, right? 0.1335. Okay, 0.1335 is not less than 0.05, so we do not reject the null hypothesis. Okay, it's a little bit of a squeeze maybe to fit that conclusion in there, but the conclusion should be that there's not sufficient evidence to conclude that the proportion of Nasonex users who experience headache is greater than that of the control group. Okay. Moving on to part B. Is the result of this hypothesis test good news or bad news for Nasonex? So I'll let you give the video a pause and see if you can answer that question. Okay, here's my response. We decided not to reject the null hypothesis, all right? If we had rejected the null hypothesis, then that would have meant that the proportion of Nasonex users who experience headache is greater than the proportion of control group who experience headaches. In other words, if we had rejected the null hypothesis, then that would mean that Nasonex causes headaches, okay? But we didn't reject the null hypothesis. So I think that's good news for Nasonex because it means that, Nasonex can go about claiming that it does not cause headaches, right? Yeah, or at the very least, it could say that there's no evidence to show that it causes headaches, right? So that's good news. For Nasonex, that's good news, right? So this is good news for Nasonex because it means that they can say that there's no evidence that Nasonex causes headaches. Part C, construct and interpret a 95% confidence interval for the difference in the proportion of individuals in the two groups who report headaches as a side effect. Comment on the relationship between the result of your hypothesis test and this confidence interval. Okay, well, so go ahead and give it a pause. See if you can do the construction and the interpretation. And then we'll talk about the relationship between the confidence interval and the hypothesis test together. But I want you to at least try to construct the interval and interpret the interval on your own. Here's my solution. So here's what we had when we ran the hypothesis test. And to get the confidence interval, I'm just going to change the type of inference back to a confidence interval. I believe we ran this test at the 0.05 level of significance. So I want a 95% confidence interval, which is what it is, what the default setting is to show us. So our confidence interval here goes from negative 0.012 all the way up to 0.045. Okay, so there's our interval. So the interpretation of this, now this is a little bit tricky, but remember, this interval is supposed to be an estimate of the difference between P1 and P2. So what we're saying is that P1 could be anywhere between 1.2%, so what we could say is that Nasonex users are somewhere between 1.2% less likely and 4.5% more likely to experience headaches as a side effect of using Nasonex, right? Okay, so we're 95% confident that Nasonex users are somewhere between 1.2% less likely and 4.5% more likely to report headache as a side effect. Okay. So commenting on the relationship between our confidence interval and the results of our hypothesis test, notice that this time zero is in this interval, right? So it's possible that the difference between Nasonex users and the control group is 0%. In other words, it's possible that there's no difference between these groups. And because it's possible that there's no difference between these two groups, we can't reject the null hypothesis, right? So we could say something like 0% is in the confidence interval. Okay, so 0 is in the confidence interval. So it would not be unlikely for there to be no difference between Nasonex users and the control group, and hence we did not reject the null hypothesis. Part D says to comment on the statistical and practical significance of Nasonex use on incidence of headache. There was no statistically significant difference, right? There was no statistically significant difference because we did not reject H null. And consequently, talking about practical significance, it's like, well, our test didn't detect any difference whatsoever. So there's clearly not going to be a practical significance since there was no statistically significant difference. So so I would just say consequently there's not a practical difference here either. I suppose what we could do is we could look at, well, let's just pretend that we had rejected the null hypothesis, right? If we had rejected the null hypothesis, then just looking at the difference here, it seems like there's maybe a 2% difference in the headache rate. That doesn't seem very substantial. So even if we had rejected the null hypothesis, I would still say And there's not like a huge practical difference. Like probably if you take Nasonex, you're probably not going to experience you're probably not going to notice a huge increase in the number of headaches that you get, right? So if Nasonex is helping you to get over some other symptom, then you could probably take it without having to worry about the number of headaches that you get increasing, right? So no statistical significance, no practical significance either. I think I said difference. I think I meant to say significance. So no statistical significance, no practical significance in this case. And maybe just to give a little like justification for that, we could say there's no practical significance either because the difference was small. And perhaps even non-existent, right? Because remember, our confidence interval contained 0, right? 0 was inside of our confidence interval. So the difference was small and perhaps even non-existent. So certainly not going to be a practical significance. Okay, part E. Note how narrow the confidence interval is in this case compared to example 1. Yeah, okay. So our confidence interval here, the distance between the lower bound and the upper bound, in other words, the width of the interval, it looks like it's maybe, 5-6%, like closer to 6%. So there's like a 6% gap here, like a 6% width. Okay, that's very narrow compared to example 1, where there was like a 32% gap, right? So the confidence interval here is much more narrow, right? It's not nearly as wide. Why is it so narrow? Well, again, I think sample size, right? Look at our sample sizes here. They were much larger than our sample sizes in the previous scenario, right? Our sample sizes were 2013 and 1,671. So I would say that's what explains it, right? We had much larger sample sizes. Okay. So that'll do it. That'll do it for this 2-sample proportion test. In the next section, we'll talk about a couple of 2-sample mean tests. And then from there, we'll talk about testing more than 2 parameters. But let's not get too far ahead of ourselves. That'll do it for this section, and I'll check in with you in the next one.